So we're all here because we want to do I/O, but we're not just doing I/O, right? That's I/O in the context of computational science. And so we've got these large experiments. We have supernovas that are exploding in stars. We've got climate analysis over hundreds of years, and these are the kind of experiments that we just can't do benchtop experiments anymore. The science goals and the scope have grown beyond where that's reasonable, either because we wouldn't live to see it or we wouldn't survive the experiment. So we're using simulation to complement our understanding of the world, and we'll see this theme as we motivate these applications. So they're trying to, these simulations are running with more sophistication, more complicated models, and so the way that we make these complicated models run faster is with parallelism, right? We have computers that have millions of processing elements, and we have simultaneous network links, and we get better performance out of storage the same way. How do we manage all that stuff? Well, you've already talked, part of the lessons you've had this week, MPI is helping to manage the parallelism at the computing side of things, and a lot of the same concepts happen in I/O. We have libraries that are abstracting the complexity, and we try to tailor those abstractions to match what the computational scientists are doing. And so that's always our goal here, is it's not enough to get good I/O performance. It's the final step on that is delivering that package in a form that application scientists, who are quite good at their application domains, but not necessarily great at I/O, can use and benefit from. So we've got to, as I said, we've changed the day a little bit from our usual I/O routine, where since we knew what to expect from the audience a little bit more, we've tailored this more to people who are coming at these high-end machines and want to get their science done quickly, and they've got an I/O problem. So sometimes when we give this talk, we've got to tailor it to people who are trying to buy machines or administer machines, but we're kind of tailoring this one to people who are using it to do some kind of application. And so that audience is coming in with one sort of mindset, and we as the presenters are coming at from a little bit kind of from the bottom up. We were going to talk about how we see the I/O models, talk about the way we think of these systems. Each of these machines are all a little bit different, but if you look at them with the right sort of squintiness, you can see certain patterns emerge. And so we talk about how those systems are built and deployed. We talk about the tools and libraries that are available to manage these systems. And then a little bit towards the end of the day, looking forward to what's going to happen in the next few years. As systems get larger and the science goals get more ambitious, the current approaches, which have had quite a long life, are going to need to be changed a little bit to keep pace with what's going on in application land and architecture land. So we have a lot of slides. If you got the PDF off of the website, it's 180 slides, but we're not going to go through all of them. There's a lot of hidden slides, so we're going to skip over some stuff here. There's also a little bit of code. There's an MPI 2 tutorial, which has an I/O using piece of it if you want to grab that and look at that after the morning break. That might be helpful to follow along. Or you can tune this out and play with it yourself. There's a lot of good stuff in there, not just I/O related. But you've probably seen this I/O tutorial from Bill and Rusty last week. Sorry, who are you? So here we have, you'll see three of us up front, me, Rob, and Quincy. And we all have been working in I/O for a while. I'm working at Argonne as a software developer. I've been there for a while. The way that the group works is Rob's kind of the idea guy. He has the big ideas, and I'm the kind of the guy that makes it happen, right? I deal with the machine specifics, I deal with the code, I deal with the nitty-gritty details. So between the two of us, we're pretty good at fixing problems. Either it requires big architecture ideas or it requires just grinding through and getting things working. So I figure whatever sort of problems you've got, we can probably make a good dent in it today. But yeah, I've worked in file systems. I worked on PVFS when I first came to Argonne, a parallel file system that came out of, Rob worked on it as part of his PhD work at Clemson. I've worked on the MPIO library. I still work on the MPIO library and making sure that it's humming along, doing the right things on these large machines, and that the algorithms and approaches there are still appropriate. And okay, right, parallel netcdf is our attempt at making an I/O library that wrapped up all these things and presented a good interface to netcdf users. We're going to talk a lot more detail about parallel netcdf later in the day. So I don't need that too much right now. But the big thing that's been really fun for me is this application outreach piece. When I first got into high-performance computing, I was working for a small vendor, and of all the headaches of a small vendor, the part that was fun was you go to different customers every couple weeks, and you try to figure out why they're using their system for what reasons, and work with them to help them, be happy customers. But when I came to Argonne, it wasn't just every 2 weeks was a customer. I could have relationships with applications that spanned, in some cases, a decade. And so it's been really good, really satisfying to get out and meet with the Flash group and work with climate people and work with cosmology people and help them understand their I/O pieces. Rob has been, in Argonne. Rob's right here in the front. He's going to come up and talk. We're going to be switching off throughout the day. And so Rob came up through into HPC by way of parallel file systems, and he's kind of the guy who runs our group at Argonne, and has been getting more and more involved in the SciDAC stuff. And at Quincy has been, it was in the university field, but is now helping make the HDF group a real grown-up company managing a piece of what was academic software. So that's been kind of a fun trail to see him blaze. I'm sure he'll talk more about that story. It's kind of right, when you get parallel SCDF, who's going to support it? Well, the labs are going to support it, and who's going to get HDF5? Well, you can contract with Quincy, and he'll support it, and he'll do a good job with that. So that's worked out really well too. And like I say, this material, these are the presenters, but the materials are all drawn from a whole host of supporting characters back at our home institutions. Well, maybe in the old days you had a supercomputer. It was a supercomputer because it was one really high-end processor or a small number of really high-end processors, and they could crank away at local storage. But as the machines have changed their model, the storage systems have changed the model, and it requires sort of thinking about the I/O stuff in a little bit different way. Again, the fundamental theme here is all these pieces and parts and storage bandwidth numbers and I/O interfaces are all there to support scientists. Either they're doing simulation I/O, they're writing out checkpoint data or history files or some piece of information during their simulation that's going to be part of the science answer, or they're doing analysis where they're looking for information, looking for science, looking for information out of there, or looking for insight out of this big pile of data. And so the approaches we devise and the outreach we do, that's all about bridging the gap between the way that these architectures are set up. Sorry, we think about applications, think about data in terms of cosmological structure or weather patterns or climate features. But in storage, you've got things as mundane as the disks, spinning disks and enclosures and RAID arrays and LUNs and storage networks. And then forwarding infrastructures, and then on top of that, there's some sort of file system and libraries. So these are all kind of, we have some more figures to talk about this. So let's talk more about applications. All right? Their I/O needs are complicated because the applications are complicated. We've got a couple examples. We draw from nuclear reactor modeling, because it's a good example of this sort of multi-scale problem. You've got something as small as a fuel pellet that you have to model and represent pretty well, but they also have things that are meters large, like these fuel assemblies, and then so you have this computational science problem that ranges from small little fuel pellets to these giant fuel assemblies, and then not only do you have scale problems, but you have component problems. You have neutron transport inside the assemblies. You've got convection of heat and fluid flow as they're generating the convection and the power. So this is getting to be a pretty sophisticated model. You have a mesh on here that is not regular. There's features and detailed things going on here. There's hexagonal prisms here that are stored in a certain way. But yet when we look at our I/O systems, we look at our file systems or our disk, the way that data is there is just a big stream of bits. There's no structure to it. There's no scale to it. It's just a plain bag of bits. So there might be a little bit of structure, right? Directories, files in that directory, but in the end, it comes down to an offset into a file or an offset into a directory structure. but that isn't really what's going on in these applications. The applications have a lot more detail and a lot more context and a lot more I guess complexity. We'll just keep saying that over and over again, right? And so, if we really want to deliver a good I/O solution to these applications, we'll come back to that later. We haven't delivered a good I/O solution to these applications. We've really got to think about how can these I/O models and I/O interfaces match an application that's getting more and more complicated. So, and not only are the applications complicated, they're moving a lot of data. Now, we're going to talk a little bit today about, through the other day, we'll talk about an astrophysics code. We'll see a little bit of this combustion code. We'll see a little bit of climate code. So even in this 6-hour day, we're going to cover a good bit of some of the large Insight applications. Sorry, Insight is the way that these applications get time on the big leadership class machines, like the Intrepid machine or the Mira machine at Argonne, the Titan or Jaguar machine at Oak Ridge. And these machines have, these applications, these projects have large computational science needs. They have to demonstrate parallel scaling and all that, but they also have hundreds of terabytes of data they have to work with during their simulation. Sometimes that's initial conditions to start to see their simulation, or it's the output data as they go on here. But they're moving. None of these are small. These are all large amounts of data, and so we have to. And if they can't move this data in or out of their simulation, they can't do science. And the whole point of these tens of millions of dollars machines is to do science. So. Sometimes I've heard people talk about I/O time as wasted time, and that hurts a little bit because I'm an I/O guy, and I don't like to think that my projects are a waste or getting in the way, but we do need to let the science progress and do so in a way that they can still, anyway, the I/O part is important, but of course, even more important is the insight gained by these simulations. So we'll talk some more about how we collected some of this data, but if you look at application behavior over time, even as recently as 3-4 years ago, the mantra was, well, we have to make checkpointing go fast. All these applications are doing is checkpointing. They are racing to a checkpoint, and then they're writing checkpoints, and then they're going back onto their simulation. And if we can make checkpoints go infinitely fast, then we can worry about nothing else, and we'll be fine. And that was, for a long time, our big comparison between, say, like the Google file system, which is read-heavy, versus simulation I/O, which is write-heavy. But it turns out that at HPC, they actually are doing a lot of I/O on both sides. Sometimes they do only reads. So this is a pretty dense sort of bar graph, but we've got applications that are the blue here is reads, and we have applications that are reading. Often, reading more or exclusively reading more data, reading more data than they're writing. In fact, sometimes not writing data at all. I think, for example, if I see, so like material science, I think that's if I understand right, the material science is reading in all these initial conditions. They churn away for a while, and they put out like an answer like, I think it actually might be like 42. Like what is the number of protons in this atom, right? So that goes out to standard out. That's not even any I/O. Some of these we've described the application in terms of science domain because we don't want to embarrass anybody. Nothing's embarrassing here, but the point is we've had to rethink we have to adapt our thinking a little bit to recognize that reading is actually pretty important in HPC. So when we have these solutions, they have to cover both aspects. We just can't ignore writes or ignore reads. And even though this data is from July 2011, I mean it still holds. We keep an eye on this periodically, but you'll find that you talk to an application and it'll say that they both have concerns about reading and writing. There's always abstraction layers in computer science. I/O is no different. On the left is sort of the big high level overview of what's going on in the I/O stack. You have the application. Like I said, applications have all these different features. They have what we call a data model, and the big challenge is how do you take that application data model and translate it into the storage data model, and then eventually into bits on the disk. And the arrows represent either either you're reading from storage going up, or you're writing data going down. But in the end, there's the application will express its data model. There will be some sort of transformation that goes on to sort of to take the way the application is thinking about data, do some rearrangements of it, or do some manipulations to make it a better fit for the storage data model, and then write out the hardware. Now, sometimes this transformation happens in the application. We often find that doesn't work out great because the applications are then focused only on specific machines. Folks like me, Quincy, and Rob, who have the luxury of thinking about portability across machines, come with libraries to do this transformation for you. But the important part here is this piece here, the data model, the transformations, the storage model. If you map that to physical hardware, this is all kind of captured in the physical layer. Between the memory pieces on the compute nodes and the disks and the I/O hardware, you have this glue, this system network, and that's actually a physical network. It's also these I/O libraries. So we're going to blow this up a little bit better. An old system, and old might not be so old, but you didn't have a terribly complicated software stack. Give me a second here. Oh, that is where it is. Okay. You would probably do all this stuff, like I said, you'd probably do all this stuff in the application level. You do some manual I/O library and write out to a file, and then how would you deal with that later? Well, you would just figure out a way to deal with it, because it was just you dealing with your own data, but mostly. And the physical hardware was pretty simple. It was your compute nodes talking over Ethernet switch. Think about the old Beowulf cluster model. It was so disruptive to the vector machines that you had cheap Ethernet switches talking to cheap disks linked together with RAID, and everything was pretty straightforward. You couldn't do too much with this. But as we update our model for the current way of thinking about stuff, you have actual libraries doing this stuff for you. You have a data model library like ParallelNet or HDF5 or something more sophisticated that is going to let the application describe what it's doing in a way that's comfortable to the application. There'll be some sort of transformation that happens. Maybe it's an MPIO optimization, or maybe it's some other middleware layer. We still have POSIX files, but now those files are, the files themselves have no structure. Of course, it's a POSIX file, but we impose some sort of structure with these I/O libraries, making them a little more portable, making them a little more self-describing. And so that's, so the logical view has gotten a little bit more sophisticated. The physical side has changed quite a bit. You have, think about BlueGene, where you have I/O forwarding nodes that are proxying the compute nodes in the storage. You have explicitly I/O servers who are attached to some RAID devices versus over a SAN, right? Oak Ridge has their Spider distributed network, and Argonne has several GPFS systems hooked up to all these different machines. So, what you might notice here is that the logical view does not make a direct one-to-one mapping to the physical view. So that's okay. That's why we have these abstraction layers. But the story is getting a little more sophisticated. So, like I said, to kind of let's see, where are we? Yeah. So to sort of restate the problem, you have the impedance mismatch between what applications want to do with their data and how their data is represented in these storage systems. And then you have the saying, a supercomputer turns a compute-bound problem into an I/O-bound problem. Well, yeah, so we sort of have that problem where we want to keep the I/O part as small as possible and then get back to the computing side of things. So when we think about how we're going to meet these sometimes conflicting goals, we think about the trade-offs, right? To have a self-describing portable file format, you may have to do some overhead, some extra conversions there to keep that portability. That's usually a pretty good trade-off, but it's something to bear in mind. And when data is, okay, so again, this goes back to the thought that maybe simulation I/O was a dominant workload. If you come up with an I/O layout that is great for writes, this is a little too loud. If you come up with an I/O workload or I/O layout that's great for the write workload, but is less good for reads, well, that's something you should be aware of, because, as we say, we were making the assumption that writes were the only workload, but now we're seeing that we have to be mindful of reads too. So that's another sort of conflicting aspect of that. And so, as I said, I've been working on this for 10 years. There's been lots of groups working on this for a lot longer than 10 years. One of the points of this tutorial and the supercomputing tutorial is to let applications people know that there is a community of people working in this I/O space. And that if you, as an applications person, who are a very clever person and probably are used to solving problems, try to tackle this I/O space yourself, you'll probably miss some detail that we've thought about in the I/O community. And so sort of these sort of discussions are an effort to reach out and make sure that people who are writing applications know who to talk to, know how to think about I/O, and know how to make the most of the existing R&D that's gone into this space. Sometimes it requires completely throwing away the old stuff and doing something new, but often we can improve what we have already, or just simply turn on a certain unknown tuning hint. Like I say, working with applications is really a lot of it is not often creating brand new stuff. A lot of it is just making use of what's already out there and in the right way. So with that, I'm going to turn the floor over to Rob, and he's going to talk more about sort of the internals, the guts of these HPC I/O systems, and how those fit into our way of thinking about stuff.
Thank you, Rob. Everybody hear me okay?
Thanks. So what I'm going to be doing, I'm going to back up to this slide for just a second. What we're really going to talk about for the next, I think, an hour, 45 minutes. For the next 45 minutes, I'm going to take an hour, but it's supposed to take 45 minutes. So we're going to really sort of be bouncing back and forth between thinking about I/O systems in these two different views. This left-hand sort of logical view of we have data in some organization in our application, and we need to get that data out onto storage or vice versa. And this right-hand view of, okay, we have this data in our application. How is it laid out in memory, and how are we going to move that data effectively from compute node memory through this complex collection of connections in these systems out to a storage system that behaves a particular way, okay? And so on the left-hand side, we're going to be thinking about how we describe things, typically. And on the right-hand side of things, we're going to be thinking about, okay, what are the ways that we can move things quickly? What are the quirks of these systems that are going to slow us down, et cetera? Okay, so we'll be sort of moving back and forth between these two views. The I/O system at a very high level, you probably already know this. It presents a file system view of data. Okay, it's the same kind of view that your laptop presents to you, right? So you have files, you have folders or directories. How many people call those folders? So when I was in school, it was directories, and we sort of looked down on the folder people. But I think lots of people call them folders now. I can't do that anymore. I have to be open-minded.
Data sets instead of files.
We have data sets instead of files if we're lucky. And so our files, it's useful to think about files as being a collection of extents or blocks or regions. We'll use a few different terms for those. And they're organized into different directories. And they all have some name associated with them. And so when we think about how this system works, we might want to know how the data is stored and organized. We might want to know what software is available beyond this sort of file model for interacting with the storage system, right? So what might we use in our application so we don't have to think about files? How data moves from some application process to the storage system or vice versa, what's involved in that process. Something that HPC people are interested in is how does this work when we're concurrently interacting with the system, and what are the quirks in that process? And then finally, what we've hinted that there are these transformations that get applied in the process. So what kind of transformations often get applied, and what are the implications of those? And why would we do that? So first thing to say, basically any big high-performance computing system you get on today is going to have a parallel file system. That's a topic I've been working on for a very long time. Parallel file systems are distributed systems, so there's lots of components. That means that they're not that reliable, which you probably know if you've ever run on a HPC system. They operate by having a collection of servers that manage a whole bunch of hardware, a whole bunch of disks and RAID arrays and network links, and coordinate access from clients. And on the software side, there'll be some software on the client, some software on the server that work together to make this happen. And a good parallel file system allows lots of clients to interact with the storage system at the same time. And we'll talk about ways that works better and worse as we go along. Now I'm nervous about hitting this button. OK, so there we go. So this is sort of a pictorial view of HPC, generic HPC system with the file system clients and servers. So we have client software that tends to run on the nodes where our applications run, although not always. And that software interacts with this distributed system that I've described over the interconnect. And this is sort of an RPC looking thing, remote procedure call looking thing. So if you're familiar with building HPC or building remote procedure call stuff, you more or less know how this sort of stuff is written. Something that's important to recognize here, unlike your laptop, every time you do an I/O operation to a parallel file system, there's a good chance that there's an RPC involved, and so there's latency involved that you might not have experienced in other contexts, and that's important. And we'll get back to that a couple of times. And then last but not least, most parallel file systems today use some sort of RAID enclosure or RAID capability at the back end to protect against disk failures. And then there's some redundancy across here to protect against server failures and things like that. We're not going to get into that piece of parallel file systems today because, frankly, it just doesn't matter as an application programmer. But if you're interested in it, we can chat about it over dinner or in the hands-on session later on. That's one difference from the way we do this tutorial at SC versus today. We sort of worth noting that on the leadership system, so this is a generic leadership system. Generic leadership system has a huge collection of compute resources, and they're blue because leadership systems should be bought from IBM. Just kidding. Sorry, Craig. Typically, in the Cray systems and in the Blue Gene systems, there are a collection of nodes that are called I/O gateways or I/O forwarding nodes or something like that that have connections to the outside world. Those connections are where our data is going to flow when we go out to this storage system. And so they are an additional hop in this network between the compute system and the storage system. So to the degree that we were accustomed somewhat to some latency in parallel file systems back in cluster systems, and I know cluster systems are still around, and that's great, it's gotten worse on current day systems and more complicated. So that's even more important. Then there'll be some external network, and usually that's InfiniBand or Ethernet, something like that. Some I/O servers, storage nodes. I'm going to use those two words interchangeably, and then some disk arrays. And so when we're doing I/O, where we have some compute nodes with stuff in memory, and it's flowing across these I/O forwarding nodes over some additional network out to some I/O servers, usually more than one of them, who are then interacting with storage arrays on the other side. So that's what we're talking about. To sort of give you a feel for how this latency matters, and it's not just latency, but it's a big factor. This graph just shows you moving 4 megabytes of data per node for a collection of nodes, 2K processes in this case, and moving that same amount of data with a different number of different block sizes. So here we wrote lots and lots of little requests to the storage system. And here we read or wrote everything with one large request. And so another way to think about it is down here we had lots of interactions. We incurred a lot of latency from lots of requests. And up here we only had one interaction with the storage system. Now we still moved a bunch of data so that there's bandwidth, but we didn't have to go back and forth time and time again doing RPCs. And so when we think about this interconnect latency as part of this model, I want you to be thinking, if I do lots of small I/Os, I'm going to be down here, and if I can group things into larger I/Os, the better I can do that, I'm going to be better off. I'm going to be up on this higher end of this curve. as is the case here, order megabytes is sort of the range you really want to be in, and that's still true today. So if you can find a way to get megabytes of data to move at a chunk in today's systems, you're ahead of the game. Okay? Now, we'll talk about how you can do that as we go here, and it's maybe not as complicated as it could be, but that's something worth kind of keeping in mind when you're thinking about how your application writes data out to the storage system. How much data are you writing? Is that sort of an effective number, or are you sort of, down in the bottom of this curve? I've said that there are these servers, right? I've flipped this around. There are these servers, and when we write to the storage system, data gets distributed. Yes. Why do we see a higher bandwidth for writes instead of reads? There are a number of different reasons that might be true. I am going to take a guess. I'm going to give you one reason why that might be true, which might have been the reason here or might not have been, which is that when we write to the storage system, oftentimes there are some persistent caches on the back end of that storage system out near the disks and the I/O servers. And so when you write into the storage system, we didn't write that much data here. It probably actually all got written into cache on the I/O servers or into cache on the disk arrays, okay? And so you can get a perceived higher rate from that than you could have if you had actually written to the disks, okay? When we read from this thing, there's a good chance that Rob went to a certain amount of trouble to make sure that he wasn't reading from the cache. And I'm hypothesizing. It's not that important that I get this answer exactly right, though. So chances are we were actually reading at least some data from the disks there. And those disks aren't as fast as that cache. And so that could account for it. Also, the read data, you get a little bit more latency because you've got to get all the data back from the storage system, and in some cases you can start funneling data out for writes as fast as you start the request. So there's a couple different reasons that could be true. It's not always the case that this happens. It's really easy to make the write performance a lot lower just by goofing with how you wrote the data, and we'll talk about that in a little bit. So you want to see this. Okay, so we've said that data goes out to the storage system. It gets distributed in some way out to a collection of servers. And that distribution is pretty important, right? Because if it were all going to one server, we aren't going to get a lot of performance when we interact with it from a large number of clients, right? So we have to get them all involved. So a good way to think about how these systems, how these parallel file systems put data onto disks or put data onto local storage. You can think about your file as being broken up into extents. So we said that before, right? And what many of these systems do, they pick some size of an extent, okay? Maybe it's 4K, maybe it's 2 megabytes, really depends on the system. That number changes over time, and sometimes you can pick one. So let's say it's a megabyte. So this E00 extent 0, we'll say that's a megabyte. And what the system will do is say, okay, I'm going to have, I've got 4 servers. I'm going to allocate some objects, some little containers on those servers, and then I'm just going to round robin extents out into those containers. And so E00 goes to the first spot in the first object or the first container. So it's on this server in this spot. And then E01 gets stuck on the next server in the beginning of its container. E02 out on the third server. E03 out on the fourth server. You can probably now understand my color coding. And as with local file systems, if you don't write into a region, it tends to not get allocated, which is a nice thing to know. So this is kind of how it works. So you can, if you know how this is operating, you can pick regions to write to so that you go to a particular server, right? And furthermore, if you know how this is operating, you can have different clients pick different regions so that they're interacting with different servers. Now, I'm not going to propose that you do that because it's a lot of work and it's different on every machine. But you can imagine now how some of these transformations might work in terms of making sure that certain people are interacting with certain servers. Okay, and that's going to be pretty important. Again, we're not going to make you code it, but it's important as a notional model. Jump to the entire other end of the spectrum. So back to our logical model. So we've been talking about sort of how the file system works and how this file system storage model operates. From the applications perspective, and Rob alluded to this, applications don't think of things in terms of files and extents and servers, right? That's not a very useful model for applications, not very portable either. Applications instead tend to have things like multi-dimensional arrays or collections of particles, right? Things like that. This example is from NetCDF. Our friend Quincy's going to talk about HDF later. And those are two good examples of models that are supported by storage software that give applications alternatives to dealing with files when interacting with the storage system. So rather than you as an application programmer having to say, okay, well, I'm going to put this piece of data at this location in a file, you can instead say, I would like to store a double precision or a three-dimensional double precision array, and I would like the dimensions to look like this, and then let me write that data out, right? And it sort of provides maybe not exactly the model that any given application is looking for, but it's certainly, I hope, a more convenient model than, okay, which bytes did I put where in this file? These models also capture the information, things like variable names and attributes on those, like units. So if you're working on a Mars lander, you can make sure that you're working in meters and not feet, things like that. I don't know how many people remember that. It's only funny because I wasn't part of the project. When we think about that logical side of the system, we want to be thinking about ways to support models like this as I/O people. And as application programmers and developers and scientists, you want to sort of be aware of what these different models are that are available that you could just take advantage of without having to write yourself. And so the second thing to say from here is that what this kind of software does is takes a model like this and converts it into offsets in a file and locations in a file in some standard way. And then you can move those files around to different places, access them from different kinds of systems and so forth, and not deal with the file view yourself. When we talk about application models, I'm going to sort of use this multi-dimensional array model as sort of a canonical example, but we recognize that that's not what everybody's models look like. And we'll talk about how to get into this model from other models later in the day. So then when we think about this software, we think about it as an I/O software stack, okay? Software stack is a collection of software products that work together, hopefully, mostly in concert, we hope. At the top of the stack, we have an application. That application is interacting with some software that supports different data models, right? And that NetCDF and HDF are examples of that. At the bottom, we have that I/O hardware and that parallel file system that's organizing that I/O hardware for us. And what we're going to start talking about are these transformations that occur, and there's software that implements those as well, a couple different kind of classes of software that implement those. And this software is what sort of gets us from these application data models and the support that we have there that's maybe been converted into a file view, file model, and gets it out to the parallel file system, hopefully keeping as much performance as we can. Articulate this goal that I think most I/O system software people have. We want, on the one hand, these data models to actually be something that's useful to our application programmers so that they're not thinking about this too much, not wasting too much time. And we want this set of transformations to be such that we get a fair fraction of the potential performance out of this storage system using these models. So not making people sort of hand tweak this stuff. Okay, so how do we do that? So we're going to talk specifically about performance tuning and how that works. When we think about concurrent access to a file on a parallel file system, which is what we're doing, a way to think about it is to think of the file as a big global shared memory region, okay? I don't know, how many people are familiar with shared memory? You've probably seen it in threads. If you haven't seen it, okay, awesome. All right, so you know what I'm talking about. So then you also know that when you interact with shared memory, the system underneath tends to have some boundaries for locking in a global shared memory system. And those boundaries may or may not be known to you. You can usually figure them out. And so when you interact with some region of a global shared memory, then underlying your application, some set of either in your application you have to obtain those locks, or depending on the implementation, the operating system may obtain a set of locks for you on the pages that you're interacting with, right? And in the file system case, it's the same thing. The file system breaks up your file into a set of regions, and when an application goes to interact with some region of a file, then all the areas that enclose the region of access have to get locked, okay? And so that's how GPFS and Lustre and PANFS and all these systems work. And they do that for so that they can provide a certain set of guarantees with respect to the view of the file from different processes. So they don't want to have different processes having different conflicting views, right? Same thing is with a strongly consistent global shared memory. Okay. The other nice thing about that is that it does enable caching, although we don't see that on some of the systems, because what happens is that you'll go to write to some region, and then the client associated with that node will just hold on to the locks until somebody asks for them back. Okay, and so in some cases we can get good performance benefits from that. Almost never works when we're writing to a shared file. And then we ask for the system will ask for the locks back if someone else asks for access. Okay. So what does this mean to us? Well, so on the left side here, I've sort of drawn some 2D views of data, and I'm sorry that the lines aren't a little bit better, but imagine a 2D array, and so here we're doing sort of column, blocks of column access, and we have happened to have picked our row links, blocks of row access, and we've picked our row links perfectly so that they align with the locks on the storage system. Okay, now that's a small miracle. But just suspend disbelief for a moment. If that were to happen, then if these processes that own these three different regions were to write at the same time, they could all get their own locks for distinct regions. There's no false sharing, and you would get the writes are faster than reads performance that we saw. That's the small miracle in that earlier graph. Okay. Now let's imagine instead. Oh, we also have a little bit of chop off on the left. Okay. Well. These things happen. Imagine instead we said, I like provenance. I like being able to figure out where my data came from and what system I ran it on and when I ran it and things like that. So I'm going to write a header into my files. That way I've got that information. So now all of a sudden that header blows our alignment. And so we're not quite aligned with respect to these lock boundaries. And so now in these areas we have false sharing. So although this process writing this green data isn't actually writing to the same bytes as the process writing this sort of light yellow, they're conflicted on this lock. And in this sort of situation, especially with a large number of processes, you're going to very quickly, performance is going to go to the tank. Okay, and so we can't have this happen. And if we do something, we say, actually our application runs a lot better if we use some sort of block distribution than if we do this silly row block distribution, which is something we learn in grad school relatively quickly. Then you get way more of these points of false sharing than you would even in this row block. So the takeaway isn't don't do block access. The takeaway is that we have to come up with some techniques for mitigating this false sharing. Right? So we can't, that's an important thing to understand if you're writing directly to the storage system, and it's an important thing to understand as a problem when we're thinking about these I/O transformations. So to sort of summarize that, we're going to have some software that sits between the application and the file system. It's going to be there to perform these transformations. There are a lot of reasons why you might perform transformations, but we're going to focus on ones to improve performance. And there's a couple things we might try to do. We might try to reduce the number of operations to the parallel file system, sort of cut down on the cost of latency of interaction. We might try to avoid lock contention, right? So try to avoid that false sharing. And then the last thing is we might try to hide the number of clients on the system. I'm going to talk a little bit about that, but not so much. That's maybe good dinner time talk, but that's something that this I/O forwarding software does for us. I'm also going to distinguish between what I'm going to call transparent transformations, so transformations that don't change how the data is laid out in the file, right? They just change how we're going to get the data into the file. And I'm not going to give them a name other than to say they're not so transparent. Transformations that mess with the organization of the data in the file. And the important distinction there is that transformations that leave the data in the format on the file system still knows what's happening with that data. It still owns the organization of that data. If we add some more software in there that changes the organization in some way, yet tries to hide the fact that it's done that, then we're going to need libraries if we move from place to place that we might not have needed otherwise. So, but we'll talk about that when we get there. So, and again, we're going to kind of keep with this model of we have a process, it has some data in memory, and it wants to put that data into certain places in a file, okay? And hopefully, by the time we get to the end of the day, you'll know that you don't have to think about that yourself that much. So one thing that we might want to do is reduce number of operations. So this is something that we see maybe on reading input files, for example. So you're reading input files and you're reading them with netcdf, and it turns out that netcdf likes to do lots of little, serial netcdf likes to do lots of little IOs. So you're not seeing good performance because it's interacting with the storage system over and over and over again. Long ago, our colleague Rajiv Thakur with Alok Chowdhury and some other guys came up with this technique called data sieving. It's a really simple idea. If we're reading, it looks like just this. You've got, wow, that could be more readable than it is, but okay. You've got some data in a file. You've got a set of regions that you're interested in that file. You just read everything in the file into a buffer and then pull out the bits that you need, right? So you maybe read 2, 3, 4 times as much data as you actually need, and then you just pull out the pieces that you need. And that sounds really counterintuitive, right? Yeah, wow, I just read 4 times as much data as I needed. But I can cut down the number of interactions with that storage system by, in some cases, 2, 3 orders of magnitude. It makes a huge difference. We'll see some examples in a second. For writes, it's a little bit more complicated because it turns into a read, modify, write process. So in the write example, in step 1, we read the entire region into an intermediate buffer. In step 2, we put our changes into the appropriate locations in that buffer. And then in step 3, we write out the entire buffer back into the region in the file, okay, including the data that we read. And that way we make sure that no changes occurred in there. We have to make sure that nobody else is interacting with this entire region during that process. So that's not a solution in itself. It's really a tool to consider, or that application teams are getting to use when interacting with these systems to reduce latency. So does that sort of make sense? So we want to get rid of latency. A way to do that is to trade some data movement for interactions with the storage system, and this technique that is often called data sieving is a way to do that. We didn't really help with lock contention in that last example. And when we think about lock contention, really we're talking about the interaction of accesses from many processes. So intuitively, it makes sense that we're going to have to organize accesses between processes in some way in order to avoid this contention, right? So another technique that is, same guys, two-phase I/O, splits I/O into a data reorganization phase, okay, and then an interaction with the storage system. And this is implemented in MPIO, but the technique is around in a lot of contexts. But the idea is, let's sort data between our processes so that when we interact with the storage system, we don't get false sharing. And in fact, we may play some additional games so that we're not interacting with as many servers, so that we have fewer requests to send. We could even throttle the number of processes that are going to interact with the storage system because we know it can only take so many at one time. So there's a large collection of different techniques that we might apply here, but the notion is the same. And so in the first phase of this, we shuffle data back and forth into intermediate buffers on these processes. And then in the second phase, these processes interact directly with particular servers or particular regions of a file that are held by a single lock. Could be either one. So this is the write version. The read version, you read the data first and redistribute the data. There's actually 3 phases here. It's called two-phase I/O because when it was written, the 0th phase didn't really cost anything because systems weren't that big. Nowadays, that phase is expensive, and what that phase is about, I'm not showing it here, is the processes communicating to figure out what it is that they want to do, right? So what I've shown here is some processes who know what data they want to exchange, exchanging it, right? But to do that, these processes first have to communicate in some way to determine a schedule, to determine what it is that they're going to receive from their partners and so forth. And as you know, on these systems, you have very large numbers of clients that kind of global communication can be expensive. And so that's starting to be something that costs time and we're aware of. Okay, but this technique generally is simple. It's let's reorganize data so that we don't get that false sharing, so that we interact with the storage system better. You don't want to do this yourself is really what this slide is about. I'm not going to go into the details of this, but you can imagine a lot of different algorithms you might apply with this technique, right? I might try to make sure that I send an even amount of data from every process, right? Because then I'll be balancing the I/O. Or I might try to align these regions that I'm going to write out so that they fit very perfectly with the lock boundaries underneath, right, for false sharing regions. Or it may turn out that it's really super important that processes only interact with one server, right? And it turns out that on different systems, different algorithms are superior. And so on a GPFS file system, you really want this algorithm. You don't ever want this algorithm, it turns out. On GPFS systems, you want this algorithm. On Lustre systems, you want this algorithm, and you want some tweaks, specific tweaks. So these algorithms are written for you in some software, but they can go awry if you don't have the right algorithm. So it's a tricky problem. I hope I'm not scaring you guys too much. All right, so I just want to show you an example. It's a little bit old example, but it is a good example of these algorithms in practice and how much they can matter. This is drawn from Jackie Chen's team. This S3D, it's a turbulent combustion code. This is just eye candy. This is from Kwanlu Ma. This is a surface drawn through this jet. It looks cool, so we'd like to put these pictures up. Anyway, then there's fire, right? Fire's great. So I guess that's context dependent. This code writes out checkpoints. It runs a long time, and systems fail, and so they write checkpoints. They've got a set of global arrays that they write, a couple of three-dimensional arrays, a couple of four-dimensional arrays, and then and these are broken up into these fixed subarrays, these little blocks. And so when they write this data out, there's a couple different modes that they write in. They actually use this library called Adios a lot of the time, but we have an MPIO version of their output that we can play with. So these are some results from that, just to give you a flavor of how much this can matter. And this first column, I'm using the term collective buffering. It's the same thing as two-phase. So this first column, we turned off the optimizations. We said, let's just let this code write without any of those I/O transformations that we just described. And because of all those little subarrays, it ends up writing 102,000 times to the storage system. They're described with 64 MPIO writes, because MPIO has this ability to describe strided accesses. But it gets translated into 102,000 POSIX writes. 2 of those were aligned in the file. They got lucky on 2 out of 100 and something thousand, right? So they got false sharing for most of them. They wrote a total of 6 megabytes. This is a small run, so 16 processes. It took 1,400 seconds for the I/O to complete at an average MPIO time per process of almost all that, 1,400 seconds. Okay, so then we turned on data sieving. Now, data sieving is going to operate a little bit better here than it would at very large scale because we don't have that many processes to contend for access, okay? Data sieve translates that into 81 POSIX writes. So we got 64 calls and 81 POSIX writes. There's some buffering going on there. It had to split some things. 80 out of 81 were aligned in file. So that's interesting. That would be worth debugging if it weren't fast already. We're trying to figure out why that one went awry. It wrote over 10 times as much data. Okay, so it went from 6 megabytes of data to 87 megabytes of data. But we went from 1,400 seconds of runtime to 4.8 seconds of runtime. Okay, so we just dramatically increased the amount of interaction with the file system from a bandwidth perspective, but we cut down the number of writes by a few orders of magnitude. right? And that's what really made the difference for us. So this was just data sieving. So now we turn on the two-phase. Two-phase converts this into 5 POSIX writes total for the entire system. And that corresponds to the these arrays plus, I believe, some header information. So we got basically a write per array plus some header. No reads. We had to do a bunch of reads over here. I didn't mention that, but of course we did. 64 writes get converted into 5. 64 writes from the system, from the application, got converted into 1 big write. Yes? So that we don't show that here. That's not actually. So thank you, Paul. So the question was, what about the communication between the processes? And this particular characterization library doesn't capture that information. It is counted in the total time. Okay, it's counted as part of the MPIO time because that communication occurs inside of the MPIO call in this case. So I don't have the number for you here, but we know that it's in that time. Okay. 5 POSIX writes. So really, what was happening was single clients were interacting with the system. We wrote exactly the amount of data that we should have written, and we got it all done in 0.6 seconds. Right. So much faster. Yes.
Sorry, could you reiterate why the data sieving, why the total rate was larger?
Yeah. In the data sieving case, because we were writing out these subarrays, imagine if you just think about this in 2D for a second, the file is laid out row major, right? And so it's reading large numbers of rows and then just changing a small piece of them. So it's that. So there's a lot of data that it's reading in order to then modify a smaller region, right? In fact, it's reading probably 87 megabytes of data in order to make 6 megabytes worth of changes, right? But that's why.
It's worth pointing out, too, data sieving is an independent operation. So each process is doing a read, modify, write of a region of this file. And its adjacent process doesn't know that its neighbor just also read, as Rob said, a row of this array. So there's a lot of duplication of effort in the data sieving case.
Now's where I start to realize I'm a little behind. But this is good. We're getting good questions, so we'll make up for it later. It's no problem. OK, so there are also transformations that occur in the I/O forwarding stage, and I want to mention those. The transformations that we just described are typically applied out here in the compute nodes and some libraries that run with your compute processes, but there's separate optimizations or transformations that are often applied or could be applied in these I/O forwarding nodes. So those nodes actually do a bunch of different things for us. The number one thing is that they bridge between these networks. So they're connected in some way to the client processes, and they're connected to the outside world. And in most of these systems, there isn't otherwise a connection to the outside world for all these client processes. So data is moving, network data and other data is moving through these I/O forwarding nodes. I/O forwarding nodes on leadership systems often also are running the client software for the parallel file system. That is always true on the Blue Jeans. It's sort of true on the Crays, depending on what the back-end file system is and how the system's been built. They can take a lot of different forms. I don't have some data on this. Reality here is that the I/O forwarding software on leadership computing machines is kind of in its infancy, and the implementations are not real strong right now, and they basically just replay whatever it is that the client did for the most part. And so right now on leadership systems, we're more or less counting on transformations to occur before they get to this phase. Research has shown that there's a lot of work that you can do at this I/O forwarding layer and that it would be advantageous to do, but it's not something that's available on the vendor systems yet. So that's all I'm going to say about I/O forwarding, I think for the rest of the day, really. I want to also mention some not so transparent transformations, and what I mean by that is transformations where the user or a library on the client side writes some data into a particular file view, and then that file view gets munged around somehow. And an observation that's sort of worth making is that we talked about this, files are sort of like global shared memory regions. Well, one thing you could try to do is just write to different files, right? Well, there are different regions, and then you wouldn't have this file sharing problem. That would be just great, right? So you can do that, but if you do that, we need then some software that would help with that probably, if we want to make it sort of transparent. And so if we did that, we would need a way to sort of group those files together. We need a way to sort of track what we put where, and a way to sort of put things back together again for the application when they went to read this data. And there's some software that's fairly popular called the PLFS, Parallel Log Structured File System. It's from our colleague John Ben and some other folks who also work with Quincy that does this. And it's been quite effective in some cases. So the way it works, it says, so we're back to this sort of simple view, processes, writing the regions in the file, rather than trying to figure out how to deal with the intricacies of the locking systems on these machines. Instead, they just say, you know what, forget it. I'm just going to take the data from process 0, and I'm going to have a folder that I'm going to write that data into, and process 0 is going to get its own file, data.0, and then we're going to store a little index that says what pieces of the file were written into this data file. Okay? And then when the user goes to read this data, we'll straighten it out. Now, this has two problems. One is, if you do read the data, you've got to figure out how to deal with these indices, and they've got some solutions to that. The other is that they've created a lot of files. And it turns out that, I'm not going to get into the details of it today, but you can also think of a directory as sort of like a global shared memory region, only the implementations of the file systems have done a poor job of managing contention on those things. And a lot of times it's one really big lock for the entire directory. And so it becomes this game of, well, okay, should I write a file per process? Should I group these somehow? And so it's sort of an open area. Really what it speaks to is that the file system model is kind of starting to fail us, and we need to do something about that. We'll talk to that at the end of the day. But you should be aware that this stuff is around. This technique can work. What we've seen is that on, for example, our Blue Gene system, we do see a lot of file per process in small jobs. And correlation is not causation, I guess, but we see this dropping off with large jobs, and we think it's probably because the users are recognizing that they're getting terrible performance at large scale with a very large number of files. There's good reasons for that. Directory operations are something that do often get cached on both systems, and they don't get cached on Blue Genes. And so the cost of creating and manipulating large collections of files on the Blue Gene is actually higher than it is on traditional clusters. But so we see people migrate away from this on their own, but probably because it really hurts them in terms of blowing hours. So we don't encourage you to go off and write file per process yourself, but to think about these components instead. One last note here. Like we've been saying, the storage data model has been this file model, this POSIX file model, for quite some time, and the file system has been the one that was responsible for maintaining it. This PLFS software that I just described sort of takes ownership of a piece of that, right? So the file system's not really entirely aware of what is where anymore. Instead, what it thinks of as a file is really only a piece of someone else's file model, and so that blurs things a little bit. Our transparent transformations sort of work within those original limits. As we've seen, there are sort of advantages to sort of blowing that agreement and taking advantage of knowledge of how this system lays things out, reorganizing things. And again, what this really speaks to is that this single stream of bytes in a file is really inconvenient for what is really a parallel thing, and for a situation where it's pretty obvious that actually multiple streams are what we want. And so we're really just trying to deal with this fact that we have this fundamental mismatch in these abstractions, right? You're at the application level, you have multidimensional arrays and many processes, and that's at least two ways to think of different streams of data coming from your application. Temporal is a third one, right? So I have time as well. So there are all these streams that we could be operating with from an application perspective. And then when we go to the file system, all we get is files and then and then collections of files. And so that is sort of at the root of the problem here. I need to move along. So just to sort of give you a picture of today, and by today I mean today's systems, I/O stack on our Blue Gene looks like this. We have, for example, a parallel net CDF or an HDF5 at the higher level that our applications are hopefully interacting with. We have a component of MPI called MPI-IO, and I know you heard about MPI earlier in the week, but I looked at the slides, so you didn't get a lot of MPI-IO. There's a piece of MPI that does I/O. We will talk about that today. I'm glad they didn't talk about it because I stole slides from that talk. I used to be part of that tutorial, though, so I don't feel bad about it. That does a lot of the I/O transformations that we've discussed. On the Blue Gene, the I/O forwarding is done by this piece of software called the CIOD. And then at the very bottom is a GPFS file system interacting with the I/O hardware. And so if you did want to optimize yourself, you'd want to optimize a line to lock boundaries, which you can find out on that system. And so this is a good sort of concrete example of an I/O stack that we could discuss. So the hardware picture, we have compute nodes, 768 cores. 768 cores out here, so lots of cores, a collection of gateway nodes or I/O forwarding nodes that are connected into these different compute nodes via optical connects, a commodity network out here, in this case QDR InfiniBand, some storage nodes. These are kind of interesting storage nodes that are kind of integrated. They're a data direct hardware product, and they're integrated with the storage racks. So we have 32 of these data direct racks out there right now, and about 1,500 terabytes per rack. Okay, so a whole bunch of disks hidden behind a relatively small number of servers. So that's the kind of system, and I don't have a picture of the Spider system at Oak Ridge, but it has many similarities to this system. So to wrap up this sort of piece, parallel file systems are what we're going to be interacting with at the lowest level. Maybe not directly, but they're there. These data model libraries are at the top and are hopefully making life easier for us in terms of interacting with the storage system. And we need a set of transformations in order to move from those abstractions that are much more convenient for us to interact with into this file storage abstraction that we're sort of stuck with for now, and still get performance. And the number of layers, I haven't said this, but you can imagine, and I'm sure you've experienced it, when you slap a whole bunch of software layers together, there are a lot of ways that can go awry. And so that's going to complicate our performance debugging, and we're going to look at some tools for helping decode what's happened later in the day. Okay, and I think at this point it's time for me to hand back over to Rob.
So when we were discussing the approach for this talk, we were thinking, well, we should show how you would use these I/O libraries in an application. But I'm just a data guy. I don't even really know how to calculate an eigenvalue or a distributed, a differential equation, right? I just know how to move bytes to storage. So I'm not going to show you how a cosmology or a astrophysics code is doing stuff. I'm going to show you how the game of life works, right? That's doesn't have any numerical methods in here. It's just a very simple set of rules. You've probably seen a screensaver that does this, or a couple animations. Right, so simple little cellular automata. Wolfram loves this stuff. Emergent behaviors out of simple rules, and it's been around for paper about it for many, many years. Simple rules, neighbors, based on whether number of neighbors, you either get lonely and die, or you're crowded and die, or you have enough free space that you spawn another person. Oh, this is animated. Is it done yet? Is there a license on the code? That's so okay. I won't go too much in here, but I will refresh this part because it kind of plays into the other sort of application problems. We have the notion of a state. There's a row by column array, but then it gets decomposed across processes, and you can pick a variety of ways to do it. Row by row is fine. Sometimes cubes or octrees or whatever. But this decomposition problem is one of the application-specific ways of dealing with sort of the global space versus a local processor. And we'll see kind of the choice of decomposition can make a big difference in your I/O performance. It also makes a big difference in your science performance too. So sometimes the ideal decomposition from a science standpoint is not ideal for I/O. These extra blue bars, so you have 4 rows on each process, but there's an extra neighbor row. The neighbor helps save some computation here. This is fun. You get this nice sort of surface area versus volume trade-off, right? If you have a big region inside, you only need to worry about exchanging information at the surface area, at the boundary. So these sort of workloads do really well in these kind of parallel environments where you're passing messages to describe the boundary conditions, but then you can work away on the local node on the interiors. Lots of ways to exchange the boundaries, which you've seen before. So yeah, so right. So we got a couple things here for the game of life. We have a two-dimensional. It's a 2D space of life, and so we have the initial conditions there. We've partitioned it across processors. We've got these boundary conditions where we're doing some method of exchanging, and then because we want our life to live on for many generations, we'll start thinking about how do we save and restore the state between runs. Answer some questions now about this first half of the session, and then we can break a little bit early and then come back, dig into the API for this game of life model. So the floor is open. What do you want to know about? A lot of that is architecture determined. Thanks. We talked about I/O forwarding nodes in the software stack in a hardware implementation of the machines. How do you pick the number of I/O forwarders you get? And on Cray, there are 14. Sorry, on NERSC Hopper, there are 14. That was kind of just picked when they deployed the system. On Intrepid and Mira, the number of I/O forwarders scales up with the number of processors you have. There are some hardware ratios. On Intrepid, there are 64 nodes for every I/O forwarder. On Mira, I think the ratio is similar. And so a lot of times, you're kind of stuck with what was given to you. And for this audience, that's true for a lot of aspects of the hardware configuration. You're stuck basically with the file system, right? No one's going to give us permission to throw a new experimental file system on their storage software or rip out the I/O forwarding layer, although we can sort of do that on some versions of Intrepid. Sorry, not Intrepid, but maybe the Surveyor machine, right? And so sometimes as an application person, you have to make use of the hands you were dealt, and some of the reasons that these software layers exist is to kind of mitigate that.